So at the end of the hour yesterday, we discovered that 1 over the velocity as a function of time is 1 over v naught plus beta t over m, right? And so the only other thing you had to do was graph it. All right? When it says sketch graphs, you do not need to include numbers. All it wants is a general shape, okay? If it wants more information, it will say that, okay? So, this one, I guess there's a couple of ways you could go about this. Option 1 is, you guys all have graphing calculators. If this is v of t, then, right? I said that wrong. If this is 1 over v of t, then v of t is 1 over that, right? So type this in your calculator and graph it. Option 2, the way that I did it was I looked at this function and I thought about what would happen for extreme values of t. So if t is 0, then, v of t is v naught. That makes sense. So I'm going to do the velocity time graph first, v t. So at time 0, my velocity is v naught, right? And then as t gets bigger and bigger, in other words, if you take the limit as t goes to infinity, as t gets bigger and bigger, the bottom of this fraction gets bigger and bigger, this whole mess gets closer and closer to 0. There's the graph. Just make sure it never hits 0. It should be an asymptote. Cool? Any problems? Yeah. All right. So, position time. Let's see. My velocity is always positive, so it's moving forward. That means my position graph needs to always be sloping uphill, right? Yeah. But it's getting less positive. The velocity is getting closer to 0, so it should be getting less steep. So your graph there should look something like this. And where you put your x-intercept is arbitrary. So you could have done this, and that would have been fine too. Okay, because it doesn't tell you what the starting position is. Make sense? So, if you did this, that's also acceptable. Follow? All right, and then for your acceleration time graph, let's see. My acceleration is always negative because my velocity is decreasing, right? At the beginning, it's very negative because it's very steep. And then it gets less steep, the acceleration's getting closer to 0, right? So again, your acceleration should start out as a big negative number, get less negative, and approach 0. That's supposed to be approaching 0. I did a crap job getting that asymptote. Cool? Any problems? All right. Finally, 2017 FRQ number 3. So we got another conservation of energy thing here, right? Which I was surprised by. So it says a uniform solid cylinder, you're given the mass and blah, 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 blah. Okay, so in my mind, there are 3 points we care about. There's here, here, and here, right? Okay. So question A says calculate the total kinetic energy of the cylinder as it reaches the horizontal table. Why does it say total kinetic energy? What's that trying to imply? You got to count translational, like regular kinetic energy, plus rotational, right? So what should the GPE, I just gave away my answer. What should the total kinetic energy be when it gets down here? The same as the GPE it had here, as long as we count this a position of 0, right? So part A, your total kinetic energy should just be mgh. You do need to take a second and find your h, right? So the height, wouldn't that be 0.5 meters, right? Because 1 meter times the sine of 30. Okay, so it's 0.5 kilograms times, you know what? You can use either 9.8 or 10. I'll use 9.8, I guess. And your height is 0.5. So this gives you 2.45 joules, right? And notice the answer key does give the answer if you use 10 instead of 9.8. Cool? Is it clear why I actually plugged in the number instead of just leaving it G here? right? Because you're given other numbers, so you can actually come up with a numeric value for your answer. Cool? All right, so that's A. B wants the angular velocity as it reaches the floor. This was a little tricky, right? So the idea is, as you go from here to here, you're converting GPE into KE and RKE, right? What happens to the RKE? I just fell over. That was embarrassing. What happens to the RKE while it's in the air, you guys? Stays the same, right? Does that make sense why that's true? All right, so really, question B, it wants the RKE here. Well, that's the same as the RKE here, right? Follow? All right. So, here's what we know. We know that the total energy is 2.45 joules. That's got to equal, at this point, there's going to be kinetic energy. And there's going to be rotational kinetic energy. So remember, I showed you guys a super secret ninja shortcut, right? I showed you that the rotational kinetic energy is equal to beta times the kinetic energy, right? I'm honestly not sure if that is acceptable. I mean, it's true. It works as long as your object is rolling. I feel like you might need to justify it, though. Okay? But the justification is super easy. Okay? Because look, our rotational kinetic energy, so this is a thing you should know how to do. You should know how to derive this. Okay? So our rotational kinetic energy is 1/2 I omega squared, right? So that's 1/2. The thing gives you I for a cylinder. It tells you it's 1/2 mr squared, right? And then what's omega? V over r, right? The r's cancel, and there you go, beta times KE. Does that make sense? So I think that is how they wanted you to do this. All right? So our calculation then becomes, so this is my kinetic energy. I got to add on my rotational kinetic energy, right? So this is 1/2 times 1/2 times 0.5 times v squared, right? Did I lose anybody there? Okay, solve for v, and then you can plug your v back in here and find your RKE. There are other ways of doing it, but that's, I think, most closely in line with the way that I've been teaching you guys to do these problems. Good? Any problems? Okay. Let's see. C, calculate the ratio of the rotational kinetic energy to the total kinetic energy for the cylinder at the moment it reaches the floor. You got to be careful here. When it reaches the floor, is this my total energy? The only force on it while it's in the air is gravity, right? So is this my total energy? Stop and think. How did I get that 2.45 joules? Anthony? Good. Yeah, when I found this GPE, I just used this as my height, right? So the idea is the total energy here is going to be equal to this GPE, right? Does that make sense? All right. So to do part, what are we on here? C? So we already found our rotational kinetic energy. So now we need to find the total energy. So the total energy at the floor. All right, that green is terrible, isn't it? Total energy at the floor is the mass times 9.8 times the total height, which is 1.25 meters. Questions, Emma?
Why is it's at the floor. So is this supposed to be GPE?
Mm-hmm. So the idea is our ball started up here and rolled down the ramp and off, right? So the GPE that it has up here is determined by this total height. The first time I found it, I just used the height of the ramp. Follow? Does that make sense, you guys? Patrick?
I have a random question. So people that grade this, are they looking...
Let me finish the problem, and then we'll do all that stuff. All right. Everybody good on our train of thought so far?
Yeah.
All right. So now I know my total energy. I had previously found my rotational kinetic energy. So now you just find a, what does it want, a percentage or a ratio? Good? All right. Now, part D says calculate the horizontal distance D. Well, look, we already found our velocity up here, right? So now all I got to do is I got to find the time. So, does anybody see an easy way to take, so, what do we got? Part D. We want the horizontal distance D. So our D is going to be whatever the horizontal velocity is, multiplied by the time that it's in the air for, right? So we already found Vx in, what, part B? So how do we find the time? Yeah, we gotta use this guy. Delta x equals 1/2 a t squared plus vit, right? What do I use as my delta x, you guys? The height of the table. What's the acceleration? Gravity, so 9.8 or 10. T squared plus vi is 0, right? Because vertically, there is no initial velocity. So solve for your time and then multiply by the velocity you found in part B. Follow?
Yeah.
Cool. All right, and then part E was just, you had to kind of select some things here. So now it says, what if instead of using a cylinder, what if you used a sphere, where the rotational inertia is 2/5 of mr squared? So part 1, is the total kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the total kinetic energy of the cylinder at the moment it reaches the floor? Well, everything else about the two objects is the same. They have the same mass, right? So you're still converting the same amount of GPE to the same amount of total kinetic energy. So it should be the same. So Roman numeral 1 is equal to, because it's still conserving all the energy. Okay? Roman numeral 2 is the rotational kinetic energy of the sphere at the moment it reaches the floor. So now we're just talking about the rotational kinetic energy. Okay? So, which sphere has more rotational inertia? I'm sorry, I said that wrong. That's a dumb question. Which object, the sphere or the cylinder, has more rotational inertia? The cylinder, right? So that means it's going to gain less translational energy, right? It's harder to get it moving, right? And so more rotational kinetic energy. And you can reference, wherever it is, that little calculation we did. I must have deleted it. Oh, this.
The college plan things?
Yeah, I was going to bring them down.
She's collecting them.
Oh, I see. Oh, where did I put them? I was going to bring them down Fort Tower. Thanks, Bob. Yeah. All right, so the cylinder, or sorry, the sphere will be going faster, which means more kinetic energy, which means less rotational kinetic energy. Cool? Roman numeral 3, the sphere will go farther because it has more kinetic energy when it gets to the end of the table. Cool? All right. Any questions on this? All right, so let me do this. Multiple choicey stuff. Let me take a minute and read through the answers. Okay? And then, do we want to do the little survey thing? Would that be helpful?
Sure.
Find out which ones people did well on and which ones people didn't. So, I'm going to multitask. All right, are you ready for the answers? So real quick too, in response to, I think, Brothy's question, was that you that asked about a reasonable score? Yes? Is that right? What's wrong? Yeah. What do I? So reasonable scores. So I just had it up. Where'd it go? Here we go. So I'll put the answer. So here it is. So first of all, this is the 1984 exam. Some of you are probably like, why the hell did he give us one that's so old? They've only released 5 since 1984. Yeah, so I don't know why that is, but they've not released a lot of them. All right. Over the course of the next 2 weeks, I'm happy to give you all 5 of those. You can practice them all. I was going to assign 2 more of them, but I can give you more if you want more practice.
Are they like comparable though?
They're comparable, yeah. Very little. The content hasn't changed.
Are they accessible to like people that are teachers?
Say that again. Shh.
If we're not a teacher, can we get to all of them and their answer keys?
I will provide them for you. Yes.
Okay.
I will provide them. All right. So here is the deal. It says that 28% of the people who took this multiple choice test, 28% of them got 24 or more right. Okay? Of those people, 83% of those people got 5s. So that should be hopefully encouraging, right? That means you can, theoretically, if you missed 11-ish, you're in good shape. All right? And as we do more of these, you'll get better at them. Clear? All right. So let me, do you want me to leave this? I think it's easier if I read the answers, isn't it? Okay. All right. So here we go. Answers. On the first page, I'm just going to read the answers. Okay? So first page is D, C, C. If we cannot react, that would help me. All right. So D, C, C, A, B, C. Next page. I'm going to put that on the floor. Next page. E, B, E.
Oh, nice.
Oh yeah.
Easiest test is wrong.
Next page.
Shut up.
Next page. A, D, B, B, A, E. Everybody good? Do I need to repeat any? Okay, next page, starting with number 16. Do I have 35? Fingers crossed? No, I got to add 2 more questions. Darn it. All right, sorry. 16 is A. 17 is B. 18 is D. 19 is D, 20 is B, and 21 is C. All right, sorry. Let's see, next page. Number 22 is B. 23 is A, 24 is C, 25 is E. On the next page, 26, I think of the ones on here, this is the one that I feel like, if you got this wrong, this one's on me. I feel like I didn't do a great job on this one. So 26 is supposed to be B. We'll talk about it.
Oh, it is.
26 is B.
Okay, yeah.
27 is A. If you got it right, then really good job. 27 is A. 28 is C. 29 is B. 30 is A. 31 is E. 32 is D. 33 is C. 34 is C. And 35 is A. Are there any I need to repeat? Hunter, what do you got?
What?
I heard you say, can you read them again? Are there any you want me to repeat? Oh, didn't you? Okay, I'm sorry. Keeper, what do you got?
28 through 31.
28 to 31, coming up. 28 is C, 29 is B, 30 is A, and 31 is E.
Can 83 be fun?
Sorry?
Can 83 be fun?
Yes. Yes. 83%. Is that maybe?
83%.
Yeah. Yeah. I mean, there's also the FRQ part. So. But yes.
Isn't the cutoff like 53%?
It varies from year to year, but yeah, it's low. It's low. Okay, so take a minute, look them over, do the survey. I've got one response here. I'm assuming that's new.
That's, yeah.
So you were saying 28% of people get 24, 84% go to. So that's like 23% get 5.
80% of, yeah. Well, no, wait. 23. Yeah, right.
Okay.
Yeah.
So 23%. That's a lot less than 6.
That's higher than I would have guessed.
It is tied up. Should I write this?
Talk is 50. Well, I haven't seen this yellow one. So I'm kind of like, you have fun now. You don't like the yellow, I feel like.
No, I don't like it. It doesn't look good on me.
See, I know. I know.
I think anyone would. Yeah, see, nobody wants to wear Miss Patrick is to Smith Owen is wearing.
I mean, now it makes really serious. What? Like how much you have. No, like Mr.
Do you just like, yeah, no, I know that, I've seen those. Yeah, no. Do you just get like a new thing or two like every time you go? I don't know.
Each time he goes, he buys like 5 things.
I've only gone like 3 times though.
So a lot. Amazon. If that one's
Five to 11 is, yeah. Preferences. Black and white, no holds, two-sided, okay. All right, I'm gonna run to the copy machine real quick and start those copies running, and then we'll come back and we'll go over some of these.
Yeah, exactly. Exactly.
It was all no. You wore hats, but apparently you
No.
I mean, you don't have my password, so. Nope, I reset my phone on after that.
Are you kidding me?
Yeah, I accidentally reset my phone a little bit. I was trying, I don't remember what I was trying to fix. But,
That's worse.
there's like a thing.
Takes it up a page.
Oh my
You
god.
can no, I just know the password.
Yeah, they don't go outside. Well, they don't you need
My
to
password is, my password is the same deal if
All right, thank you for your patience. Sorry I didn't have these ready. All right, what do we got?
Trying to learn.
Okay, so it looks like 13. We had some questions on 13. Ah, there we go. All right, so let's start with 23 and 26. Is that the one with the police?
The spring with gravity.
Oh, yes. Yeah, this one took me a little while to kind of parse through what they were talking about. The wording on it is definitely weird. All right, so let's see if we can kind of simulate what's going on here. All right, so the idea behind this one, behind 23, is this. It says a 0.1 kilogram Bach is attached to an initially unstretched spring. So it's this. Guys, listen, please. Initially unstretched spring with a force constant, blah, 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 as shown above. The block is released. So it's this. It started out not stretched and then released. Okay? So it wants to know the amplitude of the resulting simple harmonic motion on the block. So, our initial position is this. And then, when you release it, what's going to happen? Well, you guys tell me. So, it's going to fall down. So, it's going to fall down, back up, down, back up. It's going to oscillate. Thoughts?
So, this is just a question. So, when it's at equilibrium, is that just like the line of like if you kind of like what the gravity for it, it's like how much that much coming out of
No, I agree with that. And that actually might be an easier way to do this than what I did, to be honest. That's way easier than what I did.
Did you do energy?
I did it using energy. Yeah, I like that better. Yeah, you're right. So the equilibrium point is going to be the point at which your net force is 0, right? So that's the point at which the force of the spring equals the force of gravity, right?
Yeah.
So yeah, that's awesome. So our force of gravity equals the force of the spring equals kx. So our force of gravity is 0.1. I'm going to use 10 for my acceleration of gravity. Equals k times x, right? Divide both sides by 40, and you get 1 over 40 equals x. So that represents how far it stretches from here down to get to the equilibrium point. Follow? There is a way to do it using conservation of energy that's a little trickier. Yes, A+. I was trying to get through it quick. So, yeah, and this would have been quicker. So good job. Everybody good with that? All right. And then while we're on at 24, at what time after release will the block first return to its initial position? Well, so it starts here, and we're looking for the time for it to go down and back up. What's the name for that? Period. So to do 24, you just want the period of the pendulum, or the period of the simple harmonic motion. So that's 2 pi root m over k. You know your mass, you know your k, plug in your numbers. Cool?
Yeah.
Awesome. All right, let's see, the next one on the list.
26.
26. Okay, so this is the one, like I say, I think I did not do a great job prepping you on finding the angular momentum of a point particle. Okay? Because the only times we looked at it, we were looking at, like, one of the common examples was Sally jumps onto a merry-go-round, right? And we treated Sally as a point particle, right? But we always did it so that at the instant of contact, her motion was perpendicular to the radius, right? Okay? We did not do any that were like this, where you've got this particle that's over here going this way with some velocity, and you want to know the rotational momentum about the origin. Okay? So this is a thing that, again, I did not do a great job explaining this here. So how do I want to say this? If you look at the equation sheet that you're given for the test, it tells you that angular momentum is, where's the sheet? How do they express it? They express it as r, as in your radius vector, cross your momentum, which means r times p times the sine of theta, where theta is the angle between the radius and the momentum vector. So this is R, P, oops, that was weird. I just made a typo while writing. R, oh my gosh, R, P is MV times the sine of theta, right? So here's my R, here's theta. Well, I guess technically here's theta, right? Because it's the angle between my radius and my velocity vector. Follow? So isn't R sine theta just going to be this? Which on the sheet is A. All right, so long story short, when you're finding angular momentum of a point particle, you measure your radius such that you want the component of the radius that's perpendicular to the velocity. Just like when we did torque, you always want the component of the radius that's perpendicular to the force, right? This is the exact same idea. Okay? So to do this, we learned that the momentum of a point particle was mvr, right?
Yeah.
What I neglected to include was this sine of theta bit. So r here has to be perpendicular to your velocity vector. So if you'd like to make that adjustment to your notes, that is 100% on me. I did not explain that. Does it make sense? Here's a real simple example of it. So, pivot point. So this thing right now has no angular momentum, right? If I have a point particle coming along at a constant velocity, right, as my particle approaches, the velocity is not changing, right? So doesn't it make sense that whether I hold the ruler here or hold the ruler over here, I'm still transmitting the same amount of angular momentum to the ruler when the collision occurs, right?
Yeah.
Does that make sense? So in other words, what I'm trying to get at, and maybe not doing a great job of, is, oh shoot, I just wanted to select the, so here's my velocity, right? What I'm trying to get at is that where the object is positioned doesn't matter. What matters is how far away vertically it is from my axis of rotation. Follow? Well, I said vertically because the velocity was horizontal. I don't know who that was that said vertically with a question mark. So
if the velocity is not horizontal, can we just do components?
correct, yeah. So like, suppose I gave you something weird where it was like, all right, here's the origin, and I've got a particle over here going this way with some velocity. Okay? Then your radius would be such that, those are perpendicular. Does that make sense?
Yeah.
Which would be a drag that, there's not enough information there, but that's the idea. Make sense, you guys? All right. All right, so let's see. The next two winners were 22 and 27, it looks like. Oops. Why do you hate me, smartboard? So 22, 35, and 27. Somebody remember that, because in a minute I won't.
Okay.
22, 27, 35. Oh wait, didn't I just do 22?
No, you did 23.
Oh, okay. Cool. All right, thank you for keeping me on my toes. 22. Oh, good. Yes, yes, yes. A gajillion times yes. Equilibrium. All right, so here's the deal. You've got this rod, right? And it's being supported by this rope that pulls this way. It gives you this angle. You don't really even need it. But so your tension force is pulling that way, right? Okay? And gravity's pulling down on it. And the question says, and you had to read it carefully, it says the force exerted on the bar at point O, where it is pivoted, is best represented by a vector whose direction is in which of the following directions. I said that redundantly, but you know what I mean. So the idea is this. You've got this, it's this. So you've got this thing, but it's being supported by a rope that's pulling up at a weird angle, right? And so it's asking about the force exerted here at this pivot point. Make sense? All right. So, first of all, what concept or group of concepts should we be thinking about to solve this, you guys? What chapter was this?
Equilibrium.
Equilibrium, right? And so when we think equilibrium, we need to think about three key equations. What do you got? Net torque is 0. Net force in the x direction is 0. Net force in the y direction is 0, right? So let's identify our forces, all right? So, forces. Well, since I need to think of in terms of components, I'm going to split my tension up. So there's a force of tension in the y direction, and there's a force of tension in the x direction, right? Okay. What other forces are there? Force of gravity, right? Does it tell us anything? Oh, it tells us the bar is uniform. Oh, cool. So my force of gravity is going to be right here. The length of these arrows have no significance. All right. And the question wants to know what's going on here. All right. So here are the three equations we have. We know that our net force in the x direction has got to be 0. Tell me something. The tension's pulling to the left, which means the wall must be pushing to the right. Force of wall in the x direction is that way. Cool? Now, we also know that our net force vertically has got to be 0. But now I'm a little bit stuck here because I know that the force of gravity plus the tension in the y direction plus the vertical force from the wall have to add up to 0. But I'm kind of stuck here because I don't know how big the tension in the y direction is, right? Follow? So what should I resort to?
Torque.
Torque, right? Okay, so let's see. So if my net torque is 0, I got to choose a pivot point. It sort of tells you what pivot point to pick, right? Really, you can pick anything because it's an equilibrium. But let's do the net torque around point 0. Okay? Well, that means then that the torque from gravity plus the torque from tension have got to add up to 0, right? Well, which component of the tension actually produces torque? Just the vertical component. Some of you guys are nodding now. What does that help us recognize? If this is L, this is only half of L, right? Right? So this has a bigger distance, which means it needs less force. Follow? So this tells us that the force of tension in the y direction is less than the force of gravity, which means it's not doing all of the vertical supporting. There needs to be more vertical supporting over here. So now I know that the wall is pushing up and that way, which is, I think, choice B.
So I'm distracted. Because it's an equilibrium, can we just set the pivot point at the center and go? It can't rotate, so you know it has to be.
Oh, that's gold! Yes! Yes. Josh just said something. I'm glad I have you guys here. Josh just said, why don't you pick the pivot point to be here? It's in equilibrium. You can pick any pivot point you want. Which way does the wall have to be pushing now to prevent rotation? Right? The tension from the cable is making it rotate that way, so you need an upward force over here to prevent that.
That makes a lot more sense.
That's super badass. That's really cool. All right, so there's different ways of doing these, but cool. Good job, guys. All right, are we good, you guys? All right. Just to be clear, you still need to go through the motions with the x components, right? Okay. All right. So that was 22. Was 25 and Or 27 and 35?
Yep.
Yep.
27, 35, 27, 35. 27. 27. A uniform stick has length L. The moment of inertia about the center of the stick is I naught. So here's our uniform stick. It's got a length L.
Bless you.
Here's this. All right. It says a particle of mass m is attached to one end of the stick. So the total rotational inertia, or moment of inertia, of the combined system about the center is what? Well, so what's the rotational inertia of this point particle? I for a point particle is mr squared, right? So for us, m is capital M. What's r? Half of L. Okay? And then so your total rotational inertia is going to be that plus I naught, which is choice A.
B and C are the same choices.
Sorry?
B and C are the same choices. That happened again in like 31, where two of the choices were
Oh,
the
that's
same.
funny.
Yeah, there are like many typos on this.
Huh. All right, finally, 35. Oh, yeah.
Yeah, I know. Because you're
All right, 35. Last one, and then I'll go grab those copies. They should be in the copy room. All right, 35. A light. So it's got the drawing up here, right? So here's the deal. The question wants to know the initial angular acceleration. All right? So angular acceleration should be net torque over rotational inertia, right? So two steps. Step one, find your net torque. So the torque from the 3m is going to be 3 mog times L, right? So that's the particle on the left. The particle on the right is going to be mog times 2L. Is that correct? One of those two torques has to be negative, right? Because they're working against each other, right? So technically, this one would be the negative. All right, so if you simplify this, it gives you mog times L. Cool? All right, now we need to find our rotational inertia. So rotational inertia for a point particle is mr squared, right? So 3mo, oops, 3, oh my gosh. 3mo times L squared plus mo times 2L squared. Should either of those be negative? No, rotational inertia can't be negative. It's a measure of resistance to change, right? So simplify this and it gives you 7mol squared. So just divide your torque by your inertia and it gives you A. Cool? All right, cool. So I'm going to run down to the copy room and grab those FRQs. They're due tomorrow. There's another one of those drag force problems, all right? So even if you need to spend extra time on that one, do so, all right? I'll go grab those. I'll be back in 1 second.
Yeah, wait, you? Are you?
All right, hey guys, real quick. I'll give you one out of the copier. Go. Sorry, I wasn't prepared to give you guys. I know, nice and toasty.
Oh, Johnny, you
Go. So what was the response on the multiple choice, you guys? Yeah, I thought so too the first time I did one.
I did some dumb stuff along the way, but that's because I was doing the first hours, so.
Gotcha. Sounds good. I'll see you then. Nope. Oh, is anybody going to see Carla later?